Okay, good afternoon, good evening, and good morning, everyone. So welcome to the last day of this discussion. So we have some exchange between organized. So today's the discussion will be organized in this way. And so the first item will be we'll have some discussions on the bulk evolution and initial spectra, but we had started some discussion earlier on Monday, but we should probably just wrap this up and define some action items. So I will take the privilege to initiate discussion and then open for everybody to provide inputs. And then the second item, closing the future remarks, and this we try to organize. So basically we have 3 days of discussions. And so the three conveners, Ralph, Rap, and Paul and Xunian will try to, each of them will try to summarize with maybe 2 most important items and topic key points, and then propose some action items we want to follow up. So that's pretty much the structure of this morning. Ralph, Paul, Xunian, if you want to add anything, feel free.
Sounds like a good plan.
Yeah. Okay. Then let's move on to the discussion or continue. I would say probably the continued discussion on the bulk evolution. I will take maybe the privilege to share just a couple of slides quickly. I hope you can see that. Is it visible to everyone?
Yes.
Okay. So I think this is probably the differences. We know that different groups employs different evolution models, and they have different models. They has the model has a sizable impact on the final status, charm quark and dimensional spectra, and even RAA. This has been actually compared or studied or compared both by the JET HQ group and also EMITA Rapid Task Force. And you see the report by York and Ming on Monday. I think this is I would say I feel it's reasonably acknowledged by most groups. And also on Monday we discussed about whether we should we should try to how do we proceed from there. And you can see actually already from I think I see from the Annual Rapid Task Force recommendations already described that the action items that we plan to do is to employ publicly available hydrodynamic or transport evolution models, which have been tuned to data with a maximum range of viable initial conditions and model parameters, or even a single one with a pre-specified tune as a single point of contact of all approaches. So as far I understand so far, and this has been proposed, but I don't think that's been executed or taking actions by this time. So the question is actually probably practically how do we proceed? And I would probably throw the floor to the experts on the serious side. Actually, this both consider from organizational point of view, but also from a practical point of view, whether what kind of approach we want to plan ahead. So I will probably stop right here and hear more comments from the audience. Anyone feel free to comment or maybe make a proposal already at this moment.
I thought I commented already during Ming's talk that in all this models, the hydro model they use here, he only plotted at TC, right? So they are very different.
That's right. Mm-hmm.
But do they? I mean, how they final spectrum compare? I mean, do they all actually agree with the experimental data?
I don't know. We do. I see they do have comparisons in the Rapid Task Force publication. I I didn't include here. I think Ming also including his.
Because there is if you only talk about just like hydrodynamics, all the hydrodynamics are essentially the same, except the parameters are different, like the initial time, the shear viscosity, the freeze out time, not freeze out temperature, and so there are only just few parameters. And now with all the advanced Bayesian and technique, those are mostly now highly constrained by all the existing data.
Mhm.
So I'm still a little bit puzzled if all those bulk hydro, whether they can describe like all this data. If yes, and then I'll be surprised why they are so different at this TC.
So it looks like people are using different implementation. If you look at the table, they're ideal and they are several different implementations. I don't see why we should use different hydro model.
Yeah.
We should just agree on one and use the same one so that we remove one of the systematics.
Can I also comment? I think here you see, for example, PHSD, which is much higher than the other contribution. And I think we had a lot of discussion at those time, because here the request was to provide a direct pine, which is in our model is incredibly difficult. And that's why I also think might be what Hinyan proposed to compare final observables would be easy. Because in our case, direct pine, what is it? At hadronization, you produce a lot of resonances, they decay, and so on. And it's hard to compare, let's say, in transport model with the hydro models. Might be final particles would be, in this case, more constructive, because otherwise it creates misleading, in my opinion.
Yeah, I also think so. So I think this probably should be done, and then I think is if that's constrained, the more proper way to compare is just look at the space-time profile of the hydro evolution and compare. That is most important to this problem, because I know that from past studies that whether you include viscosity or not, like whether you use ideal hydro or use viscous hydro, which actually makes some significant have some significant effect on the final, at least jet quenching. I'm sure you will also have effect on the heavy flavor.
Mm-hmm.
So maybe we can all agree to use just one, hydro, which has been, other groups has been specifically spending many, manpower to trying to do constraint. So we just use that model. But the problem, I think, is that with some of the model here, like PHSD, you don't have this hydro. All you have is this transport model.
It's a transport model, but for hydro, what we can do, we can provide, let's say, transport coefficients.
But yeah, but I think eventually, the other transport models and ideas also want to try to reproduce the final state particle spectrally for the light particles. And the goal is the same. And
absolutely.
Right.
Right.
So, but one has to be careful as well, okay? The precise reason why we have asked that we provide here the particle right of the freeze out was precisely not to mix up with all the dynamics of the afterburners, we can modify
it's
those.
impossible. Look, Paul, it's slightly different treatment. For example, it depends how you do this freeze out. Some also, I think, in Hydra model, you can do that in the resonances, let them decay and so on. And here we had, when Taiso did this task, we had a lot of discussion what to interpret like direct pines, because after that we still have our string, our resonances, and partially we account the decay as a direct point. And that's, I think, the main reason for overestimation, because if you compare to final observables, we are rather good describing data, and it's difficult for us to be exactly the same like in this comparison.
But I want to insist that I think that most of these models which show some diversity here for the specific observable might not be relevant for all the models. If you look at the end, they are much more compatible with the data. But here, this diversity also reflects somehow the effects that you had on the charm quark until the freeze out. So it is important not to hide this.
Well, I don't think so again, because pines, it's very specific things, and all depends how you do particularization procedure. And maybe in quark-gluon plasma, it was even all okay, let's say, but when you transfer it to hadronic degrees of freedom, all depends on the details, what actually you're doing in each of this model. Maybe it's also origin for the differences between, for example, Nant, Catania, or for example, other models.
I'm not Elena, I'm not claiming that the direct pion is the best observable in order to interpret what the charm quark have undergone. And indeed, I mean, Xinian has advocated for direct profile and things like this. At the time, it was the best stuff that we could find. I'm just advocating for the fact of not plotting things at the very end of the collisions and still trying to look at the phase that has the most impact on the heavy quark. That's my point.
I see your point, of course. I'm fully with you that it has a big influence, but I was also thinking what to do. For example, if you plot energy density, well, it's also not very constructive, because, you know, you can interpret it in a different degrees of freedom. If you plot number of quarks, that we had also this discussion, it's also misleading, because it's again depends how heavy are your quarks or gluons or whatever, or massless, and then it's again would be some different things.
But Elena, these differences are precisely the ones which affect the heavy flavor transport, right?
Absolutely.
If you have twice the number of quarks in the system, of course you get a twice larger transport coefficient, right?
No. Look, Ralph, it depends how heavy are your quarks. Of course, if you're in PQCD, if you're in a PQCD and you suddenly have twice more quarks, I am fully with you, then it's absolutely the reason for the differences. Yes.
Yes, but these differences are very critical for the quark-gluon plasma transport of the heavy quarks. And I don't think we should shovel them under the rug just by looking at final state observables, right? That was the idea.
No, I'm not proposing that at all.
No, I'm not saying you do, but I'm just, trying to reiterate the idea of getting closer to what actually matters for the heavy flavor transport in the QGP. Maybe the direct pions wasn't ideal for that, but if it comes down to the partonic degrees of freedom, it really matters how they are modeled, and that I think needs to be exhibited, because it's a significant uncertainty.
Absolutely right. That's exactly what I said. Absolutely. And maybe in this case, look, we have a few types of model with the quasi-particles and with a PQCD type of particles, or we have a hydro just with transport coefficients. Maybe in this case, we have to separate them by 3 classes, because then you can compare apples with apples. For example, if you have just hydra models with transport coefficients, then you have to compare the time evolution of energy density, right? That's what is important for dynamics, and maybe velocities also. That's sometimes also a good idea. Then you compare just hydros, right? And then you compare separately cross-section for interaction of your charm or transport coefficients, depends if linearized Boltzmann realization or just transport coefficients, I mean, Fokker-Planck or Langevin approach. And for, for transport model, maybe you do two types, compare PQCD type of models and quasi-particles. And then you're right, then it has a meaning to compare the number of quarks. Then it's okay.
I have another proposal.
Okay.
If you basically you start with a heavy quark at rather large velocity, okay? So basically starting from 2 GeV on. Then basically, and you forget basically about the force or whatsoever. So the guy typically travels over a straight line, okay? And then what we could do is we simply kind of make the integral of various quantities, for instance, like the temperature, along such straight lines, okay, that we dig. So basically you shoot kind of test particles that are going at the speed of light, and then basically you see what is the average temperature that these lines accumulate along the QGP. And then we will compare whether, depending on the model, it's first high temperatures and low, and how long it lasts, and things like that. For me, this is the best thing that is kind of comparable to what a heavy quark is seeing in the QGP, and still simple enough to be plotted easy.
Yeah, not even average, but really the distribution of temperature as a function of time that the heavy quark moves through, right? That's exactly what you're saying.
Exactly. Then first we can start at the center of the QGP, which is of course not representative, but at least this is the first thing that we can do. You just shoot lines in each direction, and you see what you accumulate. And then the second stage, we can take some kind of initial heavy quark special distribution that will be the same for everybody, and then you look. And I think it will bring much more information.
I agree. I think the parton density probably is more indicative of the difference that has impact on this heavy flavor transport.
Yeah, it's a good idea. Maybe we should start all with the same initial conditions. We can provide that as we did for our study, or also what Stefan Bass group used, also Trento initial condition, which is also very popular for hydro models. Then it would be good, two types of initial conditions, for example.
Yeah, that
definitely can be done.
We have to agree on. I think in the interest of time, we should probably move on.
But do we have basically already action items or proposals now? And so we mentioned, and there's one approach that Paul proposed, Paul Xingnian proposed to look at the profile of the evolution and with kind of caliber probes, right? And maybe Xingnian, Paul, if we can maybe follow up later on, try to write down more precisely the request, and we can follow up after workshop to.
Sure, I volunteer for this.
Yeah,
no problem.
And this is certainly very nice actually to check the difference between different models. Regarding the recommendation now from the EMI task force, and do you think it's still worthwhile to try for each group, or I'm not sure whether practically it's easier for every group to take one hydro model to do all that?
Xin, can I just comment on this? I think for most of the models who use hydro anyway, and there is no point of comparison. We just I think there's no point to compare, because we just we can just use the the hydro people have developed a constraint or the best already. I think that the thing is we have to compare one of this hydro, for example, to this dynamic model that people use, like this PhD, or I think Catania model is also like that too, right?
Yes.
Yeah. So I think they probably the comparison is only makes sense for use a standard hydro compared to these two dynamic models, because all the other model we can just decide to use the hydro model.
Okay. So first step, as we just discussed, we look at the profile, comparing the standard maybe hydro with respect to each of the each model calculation. Sounds good. Okay. Thanks for the discussion. And Okay, that's more. I have one more just to point. This point could be very quick. It's about initial spectra. I think seem to be also well accepted that we see that PQCD or phono describe actually the charm spectra.
But Xin, sorry, Xin,
yes?
you were about to discuss hadronization, no? Or am I wrong?
No, I'm not
Sorry.
touching that. No, that's not a, yeah.
Sorry, misunderstood.
Yeah, so this actually has two parts. One is a cross section in PP, the other one is some potential nuclear PDF in AA. And on the PP cross section, I would probably advocate what Andrea was advocating on Monday. So currently the experimental data, particularly on the PP collisions, you can see is quite precise. And the point I want to say is compared to phono, if you maybe look at this middle panel, you can see actually it is not at a central value of phono, it's a bit higher, but for maybe IA, which is not particularly critical, but the shape also has a slight difference when you move to very low PT. And so I'm not sure how much this will have impact on the final IA, but since the data has now much better precision and compared to phono uncertainties, I would say it's I think practically I think as an experimentalist also point of view, maybe want to advocate we can just use experimental spectra as an input and to do the calculation, even can also coupled with some of the uncertainties that experimental can provide.
The problem is, of course, how you convert the charm quark into D mesons. So there must be some modeling, or do you propose just to bin the experimental spectra? And I mean, it's not really possible because what you start with in the theory is with charm quark spectra, right? And there will always be that gap how you convert those even at the very initial, in PP to D meson spectra that you can then compare to data. So maybe one could use a best fit of funnel to experimental spectra. Mm-hmm. And then use those charm quark spectra as a start for the transport evolution.
Yeah, I understand. Certainly, there's hadronization involved there to potentially at the low PT also become a little bit complicated. Right? It's not exactly from.
I saw your
make a comment here? But directly to that, I would have a comment that there will be very soon an Ali's paper that measures in PP5TV the complete fragmentation of charm into various mesons and baryons, and then you can use that. Mm-hmm. So I hope still by SQM this will be on the internet.
Yeah, so the question is a very low PT part, right? So whether this fragmentation picture still works.
Well, the D goes to 0 practically. The lambda C has some amount of extrapolation. But then you can take for the PT extrapolation, you could take funnel, right?
Mm-hmm.
I saw York has his hand up.
Oh, right.
Oh, so it was a while ago. So you use those different.
Okay, if not, from the talk given by Guang Yu yesterday, he mentioned that there's another problem with this, because in their latest study they find that in next leading order calculation, you also have to take into account the splitting from GLUE to CC bar, especially the asymmetric splitting. And in that case, that you have to take into account the energy loss of the GLUE before they convert into CC bar, and then CC bar lose energy. So I wonder how we actually take that into account in this test, to test in the testing of this initial spectrum here. I maybe this is the only not many people have this. It's only the calculation that Guang Yu and Sansen have done. I think most of other calculations, they probably don't have this energy loss there. Most of them just take whatever they the heavy quark spectrum from the next leading order program they have, and then propagate them through the medium.
Right. You know, this sounds like this is seem to be still, my understanding, still under development, right? I think this this probably coupled with what the time frame of this splitting, and then the energy loss of the gluon spent inside medium versus charm quark spent in medium.
Yeah, yeah.
It's
but it looks like it's quite important, especially at low PT. I'm not talking about like few GeV. I'm talking about like 10, 20 GeV. If you go to extremely high PT, essentially it's become more important. That's why you see the degeneracy between B quark, C quark, and light quark suppression at very high PT.
But you see, Xin, before we go for this specific effect, I have basically a very stupid question. So in initial spectrum, we all agree is probably not the most interesting part of the thing to model. Okay, okay, let me use a short. But then we will say, okay, let us all go for FONL, or let us all go with this experimental blah blah blah, and then we know that in the end, in the codes, okay, there will be 20 different implementations, okay, with some errors. And then for me, maybe a question to see whether we are a mature community or not is to know whether there would be a couple of individuals, okay, who would volunteer to provide basically this initial spectrum for the full community, and then we all use this, okay? And now after this, everybody is free to have its own variation and to implement, for instance, this initial energy loss. But for me, it would be very efficient if we could have a real kind of working group, okay, with several people in charge, for instance, of this initial spectrum.
Yeah, I think maybe we should all agree to use some kind of like some agreed on initial spectrum to carry out the further simulation, and then we compare. But later on, after we finish all of that, we can come back, say that let's look at specifically what is the uncertainty that we will get by varying this initial spectrum within different models.
Yeah, but I mean, a part of this has been done by the BAS group, by Yingru. I mean, there were different initial conditions, different transport coefficients, different hydro kinds of approaches, and one could switch from one to the other. This initial condition with this hydro and this interaction between the heavy quark and the plasma. So up to the hadronization, this is possible, and I think everybody can join there. I don't know whether Stefan is just right now here, but it has been done by his group, and so I think up to hadronization we can switch, and everybody can join in the standard way. I think the big problem right now is hadronization, because there we see it has a lot of influence on the V2. It has also a lot of influence on the RAA, and for this reason, there we should bring our different approaches to a common, let's say, a general approach up to the hadronization. That means we deliver a certain distribution of cells in the hydro, and from this on, every group has the right to put his own hadronization into this frame, and then we see what the difference of the different approaches are. So we are sure that comes only from this hadronization and not from other different things. And if we have understood this, I think then we can continue then to discuss which kind of hadronization is the best one, or what we should like to do as a common effort to get somehow this on a common footing.
So can I have a comment? So I think the initial spectra is pretty important. I mean, not because especially at a low PT. I mean, a low PT. Because that's the region when you have a very large uncertainty. Actually, when we have paper showing that if to try to explain the lambda C/D ratio, which so at HC it's smaller and at RIC is larger. Actually, can be well explained by taking into account the difference between the spectra at LHC and RIC energy. So the spectra, initial spectra of the charm spectra is actually very important. So I think we should try to fix that. I mean, at least you have to be able to describe the PP data. I mean, if you want to.
Yes, I think we should decide. I mean, also there are two options basically. So one is that we understand the different parts of the different programs, and the other is that we would like to describe the data. But we should not mix the both, I think. So, I mean, it's very fine if we said, okay, we optimize now the models in order to describe the data, but it's also, I think, very important to understand what the different mechanisms in the different programs actually provide for the output of the program itself. So what different fragmentation, what different coalescence models, what different interactions do. And this we can only understand if we do it step by step. And at the end of the day, we know what these different programs do. And then we can try to find a common solution which everybody shares then finally.
Yeah. So let me probably take the communal privilege. I think my understanding is this is a potential have an impact, but I think we have more. I mean, we probably want to separate the issues. At this point, I guess most groups are dealing with at least the implementation of the charm quarks going through the medium. I think the gluon contributions probably we have to see the development. So, but maybe just try to understand difference between different groups, as also proposed already. At this moment, we use say follow-on curves as a starting point. Everyone use the same calculations, and then I think as Paul proposed, we can later on follow up, trying to find any volunteers trying to work on particularly the tuning of the spectra in the initial PP spectra, try to match the experimental data, and then follow up, and then if that is implemented in place, everyone also can start to use that. Yeah. Does that sound okay? And
I agree.
Yeah.
Well, I don't see a justification for funnel wants to have data. You must respect experimental data.
Mm-hmm.
And then if there's a region that is not covered in PT and so on, you can extrapolate using funnel. But you should not use funnel if you know, for instance, that it is not describing experimental data. That really would be a mistake.
No, I fully agree. And that's why I think we had the suggestion that we use a funnel tune that makes 100% sure that you describe the experimental data as far as we in the best way we have them. Because we need that step to unfold, as Yanji also points out in the chat. For the models, we need to unfold from the experimental data down to the charm quark, right? And I think there will be some model dependence, so we cannot avoid it, right, at this point, I think.
Yeah, that's understood. However, it will be difficult for the baryons.
Yeah, so I agree, but I mean, we need some starting point, even if it's not the optimal one, but we need some common ground. I think that's the main goal, go with something which does the best job it can, even if it doesn't do the best job for the purpose of having a common ground. I think that's the main issue, that we really start with the same charm quark spectra, which are motivated by an optimal fit to PP data.
But you could, for instance, use the spectral shape from funnel, but the fragmentation function, I really think you must respect what is measured. And sure, there's no problem for everybody to do this.
Right. So yeah.
I mean, this paper will really be on the archive, I hope, before SQM, or at least very, very close. So we are talking about.
I fully agree. We we should everything gauge to experimental data as we can, but we need some model input to unfold the underlying charm quark distributions from that. And I have no particular preference, but it's still inevitable.
Well, the best is to unfold the best measure spectrum, right? I mean,
Sure.
current one, that is D0.
Sure.
And then,
Yeah, I'm not going to argue at all about not using the best data. No question.
Yeah,
But
I
we
think
need to agree on some model, and that doesn't necessarily have to be the best and greatest to at that point, because we're probably not going to agree on that anyways. But we need something to unfold the charm quark distribution that everybody can use.
Yeah, so that for that we'll need the fragmentation function or heteroization mechanism, which can vary between models, right? So that can be the uncertainties. All those models are aiming to.
Yeah.
Well, yeah.
It'll vary, but I mean, for the purpose of moving on, we just need to agree on one of them, right? And it doesn't have to be the best one or necessarily the one that everybody would agree on, but just to find some common ground so we can move on and eliminate, at least for the model comparison,
I think
that input.
No, but the initial spectrum in FNL comes with a specific fragmentation function. So if we want to be sure once and for all that unfolding the experimental data with a tuned FONL, this means that we need to agree on a common set, also a fragmentation. Then after we can vary the fragmentation if we want, but for the purpose of comparing, I think it needs at least to reproduce that when we do it in the PP, we reproduce the same. Otherwise, we are lost.
Sure, sure. But I'm saying it's not critical right now that we use the best unfolding. We should use the best data, but on the unfolding, there will be some uncertainty, but we should just use one to be able to move ahead and not get lost in the systematics so that we can come back to later.
Ralph, I'm sorry.
I think I agree also that I think Yan Jie also proposed that in the chat. I think we just start with one choice, and we can come back for systematics at the end when we finally have this plot of transport coefficient extracted. We should be able to put like error bars on each of the systematics at later on.
Yeah, but you also have to take into account because let's say if you want to use a funnel to unfold the parton spectra, right? Then later on you use that spectra, but you use a different hybridization scheme. Then you won't be able to describe the PP data. So you have to kind of first fix the hybridization. If the experiment can measure the fragmentation, then we can just use that as an input. Then unfold the parton spectrum.
Yeah.
Yeah, frankly speaking, I don't think it's very critical what happens at low PT, because simply of the fact that at low PT, we have very strong interactions and we're getting relatively close to thermalization. I don't know how close, but relatively close. And that wipes out a lot of memory at low PT.
Yeah, but in the array, you are sensitive nevertheless to what you put in the denominator. I agree with you for the numerator.
No, denominator are data, right? Point. Okay. It's full stop. The denominator are just data. Data.
Well, I never do this. I never do this, but.
Yeah, I mean, if your spectra are different, then your degrees of normalization will be different. So, I mean, we do see the difference. As I just mentioned, we do see the difference when we calculate.
If you're talking about the difference in the denominator, there should not be one because we're just using experimental data, right?
So when I say d lambda c over d ratio is not, there's no denominator. I mean, it's just a ratio in the AA.
Yeah, Guangyu, I think I see this is going to be not just a one try. It's going to be iterative, probably.
I agree.
Let's first separate this out, and we have a common ground that at least we can compare more different calculations for the following following evolutions. So otherwise, it's hard to understand the difference in the later part. So, and certainly the developments to understand the baseline, this PP data, and the fragmentation is an important part as well. I think everybody agrees, and that should be also we're going to be a different development later on. We should, as Paul mentioned, we should probably as any dedicated people to do this study, and then later on we can replace the baseline with a new updated calculation. So. Okay, I think we probably should wrap up on this topic, and that's all I have. And then let me stop share. And Ralph, I think maybe we'll just hand this to you and Paul and Xinyan to discuss about the key points from the last 3 days discussion. Do you want to start?
So I would say, since we really don't want to make it too long, that each of us, Xinyan, Paul, and myself, reiterate in really no longer than 10, maximum 15 minutes with a sharp cut of what we thought are some of the main issues that remain, and then maybe come up with some action items from the discussion. So you can start in any order. If you want to go by the order that we had it chronologically in the conference, I'd be happy to start, but anybody else can also start. But really, I think we should limit it strictly to 15 minutes each of those 3 sections. So does anybody want to start, or?
No, go ahead, Art.
Okay.
Why don't you go ahead? Yeah.
Okay. So then I'm going to share. So I actually just wrote it up in a couple of bullets. So let me share that. And you guys can say it in words, doesn't matter, I think. So I'm going to share my 2 bullets, really, more or less, for the heavy quark diffusion coefficient. And my main, takeaway or plea or suggestion, however you want to call it, is that we should make an effort to try to constrain the models completely independent of what happens in the heavy ion environment. The part of the models, of course, that can be constrained. So in that, in my opinion, leads to 2 main issues. One is the momentum dependent of the drag coefficient. QCD, there is an answer in QCD, and I think we should make an effort to get there without having to refer to data in the first place. Of course, at the end, that will be a constraint, but I think first we should make an effort to constrain it from theory and general principles as much as possible. And really, as is the case with the other components, we should probably find some common ground in that we can test the impact of the different microscopic ingredients, such as the screening mass, or more generally the polarization tensor, what coupling is used, what's the impact of the heavy quark mass, or the interaction potential between heavy and light, and how exactly the kinematics of the thermal proton properties figures, because it will make a difference if they're heavy or light, or if they are spectral functions. So all these kind of issues should I think be better understood and to some extent systematically deconvoluted, and then maybe we get a clearer picture of what they do and what maybe is more reasonable or less reasonable, because sooner or later, we have to face a choice. Then, of course, there are, and there is guidance from lattice QCD. There's a lot of lattice QCD data in the heavy quark sector on correlators, free energies, and things like that. Correlators not only come these days as a function of Euclidean time, but also as a function of a Euclidean spatial distance, and that is, of course, the conjugate variable to the momentum dependence. So even lattice QCD, and if you push maybe our lattice QCD colleagues more, we can even get more information than is already available in that direction. And of course, we need the lattice QCD guidance also for the non-perturbative effects that refers to the absolute magnitude of the transport coefficients. So these were my 2 main ideas or upshots that occurred to me after the Tuesday discussion. And please chime in now.
Yeah, Ralph, you mentioned the spatial correlators in lattice QCD. That's of course right. But even temporal correlators we can calculate at finite momentum. In principle, I have some data on disk here, but have no spectral function which I could use to fit them. So that's all possible and should come from lattice, of course.
Yeah, I fully agree. Actually, we have been looking at those. The temporal correlators at different momenta are also extremely useful. thanks for pointing that out. And
yeah, we have it for charm and bottom in quenched, and in the near future we also will have that for full QCD.
Yes, that is totally great.
That's also one could.
Yeah, these temporal correlators as function of momentum may be even more useful than the spatial correlators, because they are
sure.
by this oscillation behavior in the Fourier transform.
Exactly.
Those are all done in Euclidean
yeah,
space.
Sure. That's all Euclidean space.
Yeah, so one has to keep that in mind.
Yeah, for sure.
Well, the nice thing is that if you have a model, you can just integrate and get the Euclidean correlator, right? You don't have to do any inverse transform or something. If you have a model, you just take your model input and rather straightforwardly can calculate these correlators.
Yeah, exactly. That's what we did so far also for zero momentum, and one could extend that easily to finite momentum once you have a good model to fit to.
I have a question, Ralph. If I go back, or it's maybe a question for all the people who presented the model on Tuesday, but if I go back on Tuesday, who are the models which, according to you, could basically follow this procedure?
Well, really, any model, right? Once you have an interaction as an input, you can calculate correlation functions, right? It's not a problem. You calculate the scattering, you take the scattering amplitude and convert that in and project that into a quantum number channel that is ideally gauge invariant, say in the D meson channel. I'm not saying there's a D meson, but you just project it into a color singlet channel to calculate the charm quark light anti-quark correlation function with your scattering matrix, and then you integrate it over energy, you get the Euclidean correlator, right, with some thermal kernel. It's really straightforward. That can be done. And that's exactly my point, that there is this information out there that it seems to me it's not very broadly used right now. That's kind of a pity, I think.
I think I would be perfectly able to do this for a model. I think.
Yeah. So we could even formulate, to begin with, we could formulate how the steps of how one would go from a heavy light quark scattering amplitude that is a basic component in calculating transport coefficient, right? One could even write out a few lines on how to convert that into a correlator, right?
I think this would be very useful indeed to have just a one-page notice on the procedure to follow. I mean, this would be very helpful.
Sure, we can do that together, maybe with Olaf and Peter and so on.
I think this is useful, especially if you look at the transport of very low PT or slow heavy quarks.
Yeah, sure.
Why low PT only? If you are going at high PT, you're still nevertheless assuming you have some interaction between the heavy quarks and the part of
but there I'm not quite sure how useful the lattice QCD can help.
Yeah, that's a question how far our lattice friends can go in momentum.
In particular, when we're talking about like the very high energy heavy quark, they are not really. They are propagating and Brahmstrom all the time.
I don't agree. I mean, even for ultra high energetic heavy quark, you exchange with the medium. Your PT or your KT exchanges are rather small. You exchange 1 or 2 GeV with the medium. We are probing the medium at rather small scales.
Yeah, so there are two momenta: the momentum transfer and the momentum of the probe.
Exactly.
Those are, of course, different scales. But let's ask Olaf directly. I mean, what I've seen from lattice works thus far, is up to total momentum on the order of 5 GeV. Question is whether Olaf can give us a gauge of how far you could push that up in the lattice.
Right.
Yeah.
It is not what I meant. I mean, what I mean is, even if you consider probes that are very energetic, you still have some kind of collisional kernel, and then you have a model behind this. It can be Debye mass, okay, as Ivan has told us yesterday. It can be something else, but still you have a model of interaction.
No, clear. But the question is how you map that onto lattice data. So the relative momentum dependence would be something which is in coordinate space, right? And then, yeah, I don't know. Then you would be led to the free energy. Actually, that's a quantity which is something that depends on R, the relative distance, and that's a conjugate variable to the momentum transfer. So again, I would like to ask Olaf: is there something like a free energy for a heavy light here that can be calculated?
No, I don't see that. Of course, what we can calculate are hadronic correlators for heavy light. But
yeah, that's what I mean. And is there something like
that we can calculate? Yeah.
But the heavy light free energy, is that something you can calculate? You calculate basically, instead of putting QQ heavy quark pair, you put a heavy light quark pair in the medium and see how the free energy changes. Is that something that can be done in principle?
Yeah,
that would be utmost useful.
Yeah, that would be done in principle. Yeah.
Yeah, that would be utmost
I mean,
useful.
I wouldn't call it free energy, so I wouldn't talk about a potential picture in heavy light. I would just directly calculate meson correlators, vector meson correlators for heavy light. And that's what we will do in the near future.
Okay.
And these can be directly compared to any model you like. Of course, here you have to keep in mind, of course, that we are in equilibrium on the lattice.
Yeah, sure. No, this is all about equilibrium. That's why I said independent from the heavy ion environment. This is full equilibrium. And that's, I think, where we need to do the constraints, right? We cannot do the, yeah, of course.
And especially for heavy light systems, analyzing our lattice data, I have no idea about the spectral functions, and I'm really have to rely on any models or perturbation theory in the UV part, of course, but models somehow in the intermediate energy.
Yeah, but that question doesn't even arise if you just put it out there as a model test. Then the model is what it is, and you straightforwardly calculate the correlator, right?
Right, in principle, yes. Mm-hmm.
Okay, so yeah, heavy light information at finite momentum would be really great.
Should we move on to the other topic now?
Yes, next topic, absolutely. Thanks for the reminder. Paul?
Yeah, sure. Am I allowed to share my screen? Okay.
Yeah, let me get out of here, yes. So please.
Sure. Let me come.
It's a very nice background.
Yeah, okay. So, well, basically, I think I made the point already during the discussion, and it seems there was kind of a consensus. It would be quite interesting to start from the same hydro and the same C quark spectrum at the end of the evolution. And when I mean hydro, in principle, I think that in most of the approach, what you would need is just a freeze out hypersurface, okay, and no more than this. I mean, it's not that you really want and need to run the full hydro. Well, I don't know. I mean, in some of the models, how deep they dive, maybe a bit before TC to initiate the hadronization. But at least this would be for me the first concrete action that I would see, and then the second one. Would be here. I mean that at least I think that when we started, for instance, this heavy quark working group, okay, the first thing that we did was some kind of a calibration let's say it could seem a bit stupid and basic for the expert, but nevertheless, we made sure that in all our code, when we took the same parameters for the energy loss, then we were really able to get exactly the same result. I mean, which turned out to be the case, but after some kind of exchange between us. And I think it would be really very useful, at least for the hadronization. And I'm more speaking here more about the coalescence / recombination. Okay, coalescence may be too specific word, but at least for all the models that belong to the same class, if we could make sure that we have all ingredients and then adopt a common set of ingredients for those models who can share them and see that indeed we recover the same things, I think it would be kind of a step forward in characterizing. As for making, let's say, progress, deeper progress and rooting with the theory, I think that is still basically not right now that we will have the time to invest this. This for me should be left for further future, once we have already accomplished the two first tasks that I have advocated. And with this, I would be done. I lost my connection, or?
No, collective silence. So do you have a concrete action item that could be realized more or less immediately?
You mean on the second slide or the first slide?
No, either one.
Well, this one, I think, is a concrete action, right? I mean,
yeah, but I wouldn't necessarily know where to start from this, right? So.
Well, I know at least that if you give me any kind of freeze-out hypersurface, so an ensemble of points, okay, time, space, and if you give me some Sequark spectrum here, then I would be myself basically ready to calculate, for instance, the spectrum of direct demesons. I mean, this I could do very concretely in a couple of days. It will not cost me too much to do this. I don't know about the other approaches, whether they can be plugged easily. But for me, it's rather concrete. And the second thing is, of course, we have to go back in the EMI report and see, because there have been some variation. Okay, for instance, Chan has introduced now something that is more something like a resonance model more than a coalescence model to me. But we should see which are the approach which have this momentum space correlation, which are the ones who are making this momentum correlation coalescence only. And then I think it would be good to intercompare the parameters and collect them and make sure we calibrate them and that we find the same thing. Okay. Now, those are just my suggestions. On the other side, I'm not a coalescence expert. I think that there are people in the audience which are much more expert than I. So it's not because I convene this session that I might have the best ideas. Okay, so feel free to contradict me and to express other directions. It's okay for me.
Paul, no problem. We don't have to justify ourselves here.
But really, I think that Vincenzo, for instance, and other people might have really a much better view of what should be done now. And
yeah, so maybe Vincenzo can say something.
Yeah, maybe, I mean, what you say, we can start always from the same charm spectrum, maybe one that is close to the RAA, but at the end is not so relevant. Use the same parameter for the Wigner distribution and see what we get for the D-meson and lambda C spectrum, starting from the same underlying C and U and the PT spectrum.
So to begin with, that would be done in momentum space or also with full component information?
I think in principle we should have an underlying something that has also the R space. Then if there are, I mean, if you there are space, maybe we can start with an homogeneous one. I don't know, just a fireball. Just put the fireball use some thermal spectrum for the light quark and use one charm spectrum for the charm.
Yeah, I think the fireball is a great idea. So we just produce a simple blast wave that you can write down in one line, and then put in some charm quark spectrum, right? Again, you know, which can have a power law, no problem, but something that may be a reminiscence of some, you know, you can even make a suggestion, some charm quark spectrum somebody gets from his approach or her approach, and then use that in the utmost simple fireball. I think that is a great idea.
One has to be careful about those blast wave models, because I think the flow of basically thermal lines is not exactly the same as one in usual hydro. I mean,
no, no, of course not. But that's the same discussion about the fragmentation function, right? So we should start. We want to understand. We don't want to understand the profile of the hydro. What we want to understand is how charm quarks react to a well-defined background through hadronization, right?
Yeah, but also for the V2, I guess. Because, I mean, finally, one of the key observers is the V2, and if we have just an expanding blast wave, then we cannot check whether hadronization increases the V2 or moderately or strong.
No, it's no problem. It's no problem to write down a blast wave with V2. It's no problem. And I fully agree that that would have to be part of it. So maybe it's 2 lines instead of 1 line. Very good, Jörg, I agree. Of course, there should be V2 in the fireball.
Indeed, it is what we do in Catania at the end, because we have a blast wave with a flow that depends on phi and try to reproduce the V2 of the transport. So just with the blast wave fit.
Yeah, so it seems, Enzo, you're the natural candidate to lay out maybe on one page of write-up how we would do that, right? Using your fireball and then asking everybody to suggest charm quark spectrum, and then asking everybody to process these 2 ingredients through their coalescence model.
Okay.
Simply the point that I wanted to make, right? That if you look, okay, at some point you have this kind of formula, and simply when you look at the freeze-out time as a function of radius, I think that in most of the hydro right now, one finds, okay, that typically the freeze-out time is the latest one at the more central point, okay? While if you start basically with a blast wave, really, then it might be the point which are the most external, which is the largest freeze-out. So I don't know. I mean, we need to check.
I'm not going to argue with you that a fireball maybe not the most realistic. But the question is if we can afford a little bit compromise on how realistic it is for the purpose of having a well-defined test of coalescence or comparison, even not even test, just comparison of coalescence models.
No, fireball is fine. I mean, but I heard the word blast wave, okay, and fireball is fine. Blast wave would not be fine with me. This is what
okay, fireball. Let's do fireball. That's what Enzo suggested, right?
Perfect. No. For me, there are really 2 points. Is that we start from a given fireball with a given spectra. It can be really simple, okay, and then we just compare all the approaches that we have as they are, as brute as they are. And then the next step is that then we adopt a common parameters for all, and then we see how we can reduce or whether reduce the uncertainties between the approach, if it is possible to choose a common set of parameters. I think there are really 2 steps.
Yes.
I agree with that. But I wonder, how do we agree on the parameters in the end?
Which parameters?
I mean, the
coalescence parameters?
Yeah. Because I mean, if we have suppose experimental distance measured all the spectra down to 0 pt, and now the question is, are we done with the hadronization mechanism study, or do we actually need other input to test our implementation?
No, I think the next step is, and Paul may correct me on that, then the next step is to also apply more general principles. And we know that most of the coalescence models do have some approximations that may or may not be good. And then we should ask the question. I think that's also what Paul mentioned. If one can find some sweet spots in parameter space that maybe not rigorously, but at least approximately adhere to general principles. Do you agree, Paul?
Yeah, sure. What I think, well, I think we should not initiate in the end how we fix the parameters. It is for me really a difficult question, especially because I think we have a bit less guidance from the lattice than for the transport coefficient. So, but it will need to come, okay? But we have to start with something, and for me, those are the two most concrete actions that should be done rather fast. And
sure, I agree with the first step.
You see, I'm also looking at the history of our field. Okay, I mean this reaction model from Ralph, and I'm sorry, I forgot the name of your collaborator.
Hendrik van Hees.
Yeah, and Henrik. Yeah, but there was a third one. But okay, I mean it was in 2007, if my memory is good. And since then, basically, we're still waiting for new developments. So it's not going so fast, but I hope it will accelerate in the upcoming years.
Oh, you mean the resonance recommendation?
Yeah, the resonance. Yeah,
oh,
the resonance.
Lorenzo Ravalli.
Yeah, exactly. Ravalli. Yeah, exactly.
He developed that. Yes.
Yeah. But okay. So Vincenzo, should we convince this, the both of us?
Yes, we can. I mean, I can start to write up something, and then I send to you, and maybe we just do some back and forth with the email, and then send to the others.
Okay, good, perfect. So at least we have at least one specialist of coalescence in the game.
So Paul, you said 2 action items. So that one I think is a very clear one with the fireball and some transport charm quark spectrum in there. What was the other one? Yeah,
the other one, as I said, was to collecting basically all the inputs of the various coalescence models, just the tables of what are the specific things, what are the specific parameters, whether there is some renormalization applied or not. I mean, this is here and there in the papers. And I think some information is already in the report. And
yeah,
then
so
decide. And then decide for those who can to apply the same parameters and then to see what are the remnants. So it's kind of calibrating to make sure that when we apply the same coalescence with the same parameter, concretely, we get the same thing, okay?
Sure, okay. So that would be step 2 after the other one. So it would be 2 subsequent steps.
Yeah, in order still to reduce indeed the diversity. Then after the question, what is the question of Gert, I asked about what would be the correct parameters.
Yeah, great. Okay. So I think we are in the closing in on the 15-minute window. Are we ready to move on this then? Paul, are we ready to move on?
Oh yes, for me, quite fine.
Okay. I also don't see any more comments. Then let's hand over to Xingyang Wang for the last.
Min has a comment.
Okay. I didn't see that.
To discern the nature of different coalescence recombination model, we may have a more direct and simple approach without looking at the area of V2 or fireball. But I'll let you read in the chat.
Yeah, okay, sure. Charm quark probability is I'd say, a corollary that we can extract. No, sure. Agreed.
I think we can simply do it for a static medium without referring to any flow effect.
No. I'm sorry. We're also in the models where the fluid velocity and things like this. Okay, I mean we should not reduce too much. Okay.
Yeah, we can play that game and put the velocity profile to 0 at some point. Exactly. No problem. But I think the way how a collective flow is converted, what the role of the collective flow and the conversion from quarks to hadrons is, I think is something we definitely need to address. Then we can cook it down. If that gets too complicated, we just cook it down to zero flow.
Yeah, especially because we have found that there might be some correlation still at rather large PT, but for this you need, of course, a radial flow. Otherwise, you do not get it. I think it's important to have this.
Yeah, no, Min's comments well taken. Okay, so now we really have to move on. We reached 15 minutes. Xingyang, please go ahead.
Okay, you will not take long for me. I just want to maybe finish what we tried to discuss yesterday before we move on to this gazetton, which essentially people have lost interest. So my point is that we know when you go to high momentum, the radiator correction to the whole process is becoming important. And then the question is that we will have to ask, how this radiator correction will have impact on the transport coefficient you're trying to extract, even though you want to extrapolate to a very low momentum, and how this radiator process have impact. So I think that's definitely is a very important area that we so far have not really seriously addressed. In the last JET workshop work group report, we specifically have really looked at this by comparing different models, and we clearly see that that the different models fall into two groups. One group with radiative correction, the other one without. You can clearly see these two converge, but very different. So, but I don't know what is the action item on this. The only thing I can think of is just for each group that we have to, if for those people who currently do not have radiator correction, they should try to put that in, and then see how that will influence the final result. In terms of checking, I'm talking about the elastic versus radiative only. One way to check is there's some existing data on the correlation. For example, for heavy quark versus light quark correlation, that potentially can provide constraint whether you need this radiator correction or not, or how important they are. I think the data from the first day we heard from Andrea's talk already. There's this in PP. They measure this called dead cone effect already. I'm sure maybe there could be down in the future there could be other measurements that for particle correlation that provide constraint about this. That's all I have to say.
I have one comment maybe. If we indeed want to check how far the radiative contributions push into the low PT regime, we'll inevitably face the question at some point, what is inverse process, right? 3-2. That's just detailed balance, right? So that would definitely need to be included in also.
Yeah, definitely. That can be included in many approaches. This is a detailed balance, yes. And the detailed balance is more important when you go to very low PT. Very low momentum is more important than high momentum, yes.
Sure. Okay, any more questions or comments on this topic?
I think that's all for me. And
frankly speaking, I mean, we do not have this detailed balance. I think up to now, only bumps have this. Unfortunately, they're not there around. But
Yeah, go ahead. I'm sorry. Yeah, go ahead.
But well, can I comment, because to
let
make
me
a
just
digital balance in 322, it's definitely known since very long, and well, for example, in PhD we have it from very many channels, and I think it's known how to do that. Formulas are there, it's possible to implement.
Yeah, it's also, at least within, I know within our LBT model, is easy to implement. We actually have some kind of radiative spectrum that exists that take into account the detail balance.
What I wanted to say that at least in our approach, we have already one answer to this question, that indeed the radiative does not have too much influence on the DS, because it's really kind of suppressed by the phase space. But it would be good indeed to have this kind of insight from different models. That's for sure.
But DS is zero momentum, right? DS is by definition zero momentum. So I don't see how there's any radiation at zero if you have a zero momentum quark.
Because you are surrounded by quarks that have a finite velocity that hits you and then makes you radiate.
Well, that's
come on. You know that, right? The radiative correction that includes also high order like virtual correction. You know, they all contribute, no matter whether you have zero momentum or not. It just you don't know how much is that. It's not definitely not dominating, like very high PT, the radiative energy does dominate, but I think it's still unknown how they will influence the transport coefficient when you extrapolate to low PT, zero momentum. So I think probably we should end up here, but what I propose is that for one of the homework we should do is for our organizer to have some kind of one-page sort of write up, the summary, and then we want to articulate what kind of homework we want to do, and then distribute to everybody else. And then we start from there.
I still have two questions. One is really specific for the radiative, and it is the question of the gluon mass, because this is really an important parameters. And I see that depending on the approach, people take either zero gluon mass or mild gluon mass, or even very easy gluon mass, and then of course the contribution that you get from the radiation really differs a lot. But don't you think that there would be some kind of common work to do about just discussing this specific point? I mean, why people believe it is good to have zero mass, and because for me, it really leads to a diversity of predictors.
Yeah, I agree. But this needs to be faced. I mean, if we if we are really in a thermal medium, we cannot ignore that the emitted gluon can only propagate in the modes that are provided by the medium, right?
Toxinian, what do you think? You have the most.
Yeah, I think so. I also agree with you, and it's just that is the mass, the concept of mass, it probably can be used when you consider everything is is in equilibrium, of course. And
that's a very good point. I mean, indeed, it takes time before you get equilibrated. So for me, I would really like to have a discussion with people that tell me whether they put zero mass, just a simple commodity of the approach, or whether it is zero because I think it is zero up to a certain distance, or things like this. I think this discussion should be really fruitful also on the conceptual level.
Yeah, I think a lot of models, they consider the mass for the exchange to glues, but many people don't include the mass for the radiative glues. Yes.
And then if we could have a discussion sometime, then maybe it would help people to make their own judgment whether or not they want to shift their position. And
okay, good.
and
So,
the other question.
In mind.
Sorry, and
Yeah.
the other question that I had, still we are still around the table, quote unquote, is what is the general feeling among the audience? I mean, about those homeworks. No, we manage basically to gather these in nice publications, which are nicely quoted. Is it also the way that we intend to do? I mean, to have this common work in the end published? Or is it just for the sake of making the field advance a little bit, but with no specific will of publishing anything commonly? What is the feeling?
Yeah, I think that's the reason I propose to have after this when we go offline, we should write some kind of summary and propose a homework for everybody to to think about doing.
Yes, but if I attend this workshop, not an organizer, but just as a kind of usual speaker, and if I hear that in the end my contribution to the homework would be converted to a publication, this basically might maybe give me more enforcement, or not the correct word, but more insight to go and make indeed this homework. I don't know what is the global position here around that.
I think that's probably that's one of the I think that's probably one of the goal or outcome of this. And of course, but keep in mind that a publication can simply arise just from one workshop. It requires all of us to continue to work, maybe
Exactly.
even more working group meetings too on the road. But I think this workshop essentially is just for us for motivate us to continue.
Perfect.
But here I would support Paul also, because for young people who work on this, for example, I know that I saw he spent a lot of time, and actually computational time, because all of these tasks are rather expensive to compute V2 or whatever, at least for transport models. So, and he spent a lot of time, and I think for other people too, maybe we would agree to write some small summary, I don't know, in the future, which could be publishable, with the present conclusion and present status of understanding where we are. And
no, Elena, I was advocating that we should write a publication right now. It was just to make sure that in the end, if we do this homework properly, we intend to publish something. It will not be just, okay.
I think right now, at least at this moment, it's still not clear to me what we're going to write about. I think that will come out maybe if we continue to discuss on this.
Yeah, sure, it could be done later, but at some point we should summarize it and keep this present homework, that it's not lost, and maybe some parts that we can include also, maybe not all, but some plots which we find reasonable. Sure.
Yes. Maybe one thing we should maybe we can think about is we discussed already. There's some kind of systematics, for example, the initial spectrum, the variation, the bulk we're trying to limit, and then the constraint from the lattice, and then radiative correction. This is like 3 different areas on the final harmonization of 5 now. So maybe we can think about working out the systematics one by one, and how much they will influence the final extraction of the transport coefficient, for example. I think systematics is very important if we want to, finally extract something, and then people only believe you if you have some kind of systematics over there.
Yeah, I fully agree.
Maybe that's something we can think about. We don't have to write on all of them, but maybe we can at least focus 1 or 2 or even 3 of them, in the near future, working from here. So I think I hand over to Rolf. Maybe you want to close out.